Hello, you are listening to Nomad of Dreams. Today, we will talk about Albert Einstein as a thinker whose modes of thought went beyond formulas and instruments. This topic is important because a scientist's way of thinking remains a model for how to combine imagination, clear principles, and attention to fact. You will receive a set of images and criteria that will help you look at ideas as answers and as questions at the same time. Where are you listening from and what time is it there now? Write in the comments. I enjoy seeing the geography and times of day of those who have joined the conversation. Take a couple of deeper breaths, drop your shoulders, and tune into an even rhythm of breathing. Albert Einstein appears to us simultaneously as a person and as a pattern of thinking practices that shape the 20th century. His figure links concrete historical circumstances with methods suited to people who aim to understand the world as a whole. What matters is not the chronology of steps, but the character of the choices. What grounds are taken as basic and what consequences are drawn from them. The approach in which abstraction leads to tangible consequences remains a contemporary strategy for those who tackle fundamental problems. At this level, Einstein is an example of how a single intellectual axis can pivot an entire scientific culture. The historical context around him was saturated with the speed of change in technologies, social structures, and worldviews. The scientific scene of his time included deep mathematical innovations and a drive to test hypotheses experimentally. The simultaneous pressure of technical progress and political shifts created an environment where theories demanded a clear connection with the observable. This influenced how one's stance is formed. The value of ideas was measured both by their internal simplicity and by their ability to suggest tests. The personality of a thinker working in such an environment inevitably absorbed the demands of the time and responded with forms of thought that combined intuition with exacting standards for results. Briefly about the man for context. His habits, preferences, and working rituals were part of the intellectual economy in which ideas were born. Emphasis on mental operations and a tendency toward prolonged internal work shaped the character of his investigations. Biographical details serve here as a backdrop against which the structure of thinking becomes clearer. The idiosyncratic way of constructing chains of thought is more important than individual life episodes because it shows how a philosophy of practical inquiry is formed. One of the central characteristics of his thinking is mathematical imagination. This is not simply the use of formulas, it is the ability to construct images that become working hypotheses and translate into the language of precise relations. Thought experiments for him played the role of a cornerstone tool. They allowed him to formulate a question in maximal clarity and see which properties must belong to a correct description. The method works like this. First, an image of a situation arises. Then, it is subjected to criticism from the standpoint of principles. And finally, the conclusions are given a mathematical shell. There is a transition from a sensory image to abstraction and back again, and meaning is born in this cycle. This practice had a clear internal organization. He strove for expressions in which the simplicity of a postulate yielded a wide range of consequences. A mimo premise turned into maximal interpretive power, if it was formulated precisely as a principle. Thus, the scalability of ideas emerges. One carefully formulated axiom can explain many phenomena. In this context, mathematics became a language rather than a set of rules to be blindly followed. Intuition guided the choice of vocabulary, and rigorous interpretation ensured predictability. At the same time, connection with experiment was important. A theory was required to propose concrete, observable consequences that could be subjected to testing. Such a criterion provided a clear guide. Ideas that produced clear empirical signs found themselves at the center of attention. This formed the discipline of thought in which the abstract and the concrete walked hand in hand. The consequence of this discipline is visible in how concepts were formed and in what form they were presented to the community. Einstein regarded theory as a tool for singling out the invariants of the world, those characteristics that remain unchanged when the observer's point of view changes. The importance of invariants lies in the fact that they provide a stable basis for interpreting facts. When a mathematical construction fixes an invariant, it becomes an effective means of communication between different observers. This turns abstraction into a public resource. Concepts that are robust to changes of perspective serve as a common support for further research. The coupling of an internal image and an external criterion of testing gave his method flexibility. He could permit bold intuitive steps because each such step had a path down to concreteness where it could be tested. Thus, a balancing structure was created. Creative imagination and careful testability mutually reinforced the practical viability of ideas. In this sense, his working style became a model of scientific thinking that continues to set benchmarks in theoretical disciplines. Special attention should be paid to the way he posed questions. Questions were posed so as to reveal the structure of possible solutions, not merely to clarify particular cases. This distinguished him from approaches that collected empirical material without a clear idea of what to do with it. The formulation of the question pointed the way to the formulation of a principle, and the principle to a set of consequences. Such a procedure makes visible how theory takes on the function of directing research, linking method with subject matter. The historical environment provided resources for such an approach. Mathematics and experiment were sufficiently developed for a thinker to realize his intuitions. The development of geometry, analysis, and measurement methods supplied the language and tools for the crystallization of ideas. This created a situation in which the philosophy of science and practical physics walked in close step. When thinking relies on available tools, it attains expressiveness and feasibility, and social conditions give value to directions that offer clear applications. It is important to clarify the limits of the method. Imagination and mathematics enter a dialogue that demands responsibility for semantic transitions. A construction born in the scientist's mind must receive an interpretation comparable to observation. Without such a link, an idea risks remaining an elegant image devoid of operative force. Influence on reality becomes possible through the conceptual bridges that translate metaphor into measurement. He took this duty seriously, and it shaped his methods of public writing and scientific argumentation. Personal qualities manifested in behavior mattered for sustaining this style of work. A tendency towards solitary work, exacting standards for clarity, and a habit of long concentration created conditions for extended mental operations. The environment influenced problem choice, but the deep-set stance set the criteria for their selection. How far the proposed question allows the formulation of principles, not just descriptions of phenomena. These dispositions explain why he approached problems in ways that extracted maximal depth from them. His communication of ideas had an explicit component of public responsibility. He could package complex thoughts into figurative expression accessible to a broad public without sacrificing scientific precision. This skill turned abstract constructions into subjects of dialogue with society. The result was an expansion of the idea's influence and an intensification of their testing through a wide range of critique and application. Words and formulas worked together, The former provided direction, the latter the form in which experiments could be carried out and consequences discussed. When it comes to significance today, it is clear that his method remains a resource for thinking under uncertainty. Principled clarity and the demand for empirical linkage provide a way to evaluate new ideas. In the contemporary scientific field, where many abstract constructions appear, an approach oriented toward establishing principles and seeking observable consequences remains a practical tool. This matters for those who aim to create theories that work not only in the mind, but in the world. Finally, it is useful to keep his figure as an example of integrating imagination and responsibility. The thinking practices he used combine artistic boldness and scientific exactitude. Such a synthesis makes possible the transition from isolated observation to a general picture and then to testable predictions. This is what one can be guided by when building robust and substantive explanations in any field where it is necessary to understand deep connections between phenomena. In his youth, he developed a sense of intellectual autonomy that manifested itself in the continual re-examination of authoritative claims and the desire to understand the grounds underlying words. This impulse, combined with a demand for clarity of formulation, any claim was subject to review by the question of what exactly it asserted and what consequences it implied. Such an approach forms the habit of choosing not merely ready-made answers, but questions that reveal the structure of possible solutions. In a learning environment, this approach looked like an internal discipline, attentive rejection of superficial memorization in favor of through-line logical coherence of concepts. School and university contexts provided him with a contrast between a system oriented toward testing the assimilation of facts and his own way of working based on intuition and critical perspective. He came to understand that educational institutions have their procedures, but they serve ends that can be re-examined. This idea gave rise to the practice of independently selecting study materials and independently constructing meaningful links between disparate topics. A habit developed of working with sources that provoke intellectual resistance and deriving productive tension from that. A love of solitude and of prolonged concentration arose from a combination of personal inclinations and the necessity of deep thought. This was not isolation for its own sake. It was the organization of space for mental operations. Rituals associated with allocation of time and attention became instruments for creating conditions for productive intuition. The stability of such rituals made it possible to return to problems from new positions and maintain an internal dialogue in which fundamental questions were born. Musical practice and aesthetic attention functioned as a break, and at the same time nourished the capacity for imagistic thinking. Engagement with music shaped another modality of perceiving order and rhythm, which transferred into the ability to discern structural relations in abstract situations. This transfer of skill from one field to another illustrates how external habits become part of the intellectual economy. Maintaining such practices strengthened resistance to routine distractions and improved the capacity for long internal work. Reading philosophical texts in his spare time gave him a set of orientations, among which the search for principles explaining a wide range of phenomena became important. The texts brought not ready-made answers, but ways of posing questions and criteria for evaluating theories. Such interaction with philosophy urged him to process his intuitions into more rigorous formulations to avoid ambiguity. Precision in the language of discussion helped separate working hypotheses from images that serve only as intuitive aids. His attitude toward authorities evolved as respect for the merits of others' contributions, and at the same time as a demand for justification of every assertion. This position allowed him to accept knowledge and simultaneously subject it to testing by internal criteria. With this approach, interaction with mentors became a dialogue in which the question set the tone rather than obedience. The habit of asking about logical grounds turned study into a series of intellectual checks, where each step was recognized by its contribution to the overall structure of understanding. His choice of research problems often depended on whether the problem was representable as a source of principled generalizations. A decision was made when one could imagine a minimal set of premises capable of generating a significant number of consequences. Such a strategy minimizes the amount of arbitrary material and increases interpretive power, since a small number of basic assumptions are easier to control and criticize. The flexibility of this strategy showed itself in the ability to switch between details and general frameworks when the situation required clarification. The environment and social context influencing the formation of habits mattered, in that they offered both models and contrasts. Interaction with colleagues stimulated the testing of ideas by word and discussion, and societal expectations pushed toward clarifying statements. In such a field, intellectual independence combined with the ability to communicate and accept criticism. A culture of argumentation arose, in which an opinion was strengthened by evidentiary sequence, and the ability to show why a particular premise mattered. Rituals of recording thoughts had strategic significance. They fixed steps that might otherwise have remained ephemeral. Keeping notes became a way of ordering intuition and testing it for logical coherence. Developing one's own notebooking practices made it possible to return to ideas with a renewed vantage point and reveal hidden assumptions. Having a written record eased communication of complex ideas to others and served as a means of self-analysis. Immersion in abstract problems was accompanied by the need to find empirical support to understand the boundaries of an idea's applicability. The search for such anchors determined the strategy of verification and helped avoid contentless speculation. The requirement to be able to put an idea to experiment means thinking with an eye to the observable, even when work is done in the abstract field. This stance shapes the pragmatics of theoretical thought, where the value of an idea is measured by its ability to come into contact with facts. The drive to simplify concepts arose from the need to make thought manageable and subject to criticism. Simplification did not mean a loss of subtlety, but a focus on the functional core of a problem. In the process of simplification, it became clearer which assumptions actually play a role and what consequences follow from them. This working discipline encouraged clarity in formulating principles and attention to their logical limits. The ability to live with doubt became part of the intellectual etiquette. Doubt acted as a way to keep the question open and avoid premature conclusions. Such a position required resilience in the face of uncertainty and a readiness to undertake prolonged internal analysis. Doubt stimulated diversity of approaches and sustained a willingness to change direction in light of new arguments. Ultimately, doubt served as a source of productive tension rather than paralyzing indecision. The style of communication that took shape in his early years combined clarity of argument and a tendency toward figurative explanation to make the complex accessible to the listener. In this combination, there was a sense of responsibility for comprehensibility that extended beyond the academic circle. The ability to transform technical thought into figurative expression helped maintain a public dialogue about science and its values. This skill refined the way ideas were presented and amplified their impact. A habit of setting research goals that could be formalized as criteria for judging correctness established a discipline in which the choice of a problem contained the method of its solution. Goals took the form of tools that could be tested in successive steps. This allowed fruitful directions to be distinguished from those that lead to cyclical descriptions. Choosing clear criteria governed the course of work and reduced the likelihood of metaphorical vagueness. The influence of literature and cultural texts brought into thinking a field of semantic links and images that supported philosophical reflection. Encountering artistic tradition made it possible to think about scientific activity as a human endeavor connected with values and ethical questions. These links reinforced a sense of responsibility for the results of thought and for its impact on society. Reading served as a source of complex allegories that helped formulate abstract ideas in an understandable form. The development of a scientist's personal ethics took place in dialogue with social tasks that carried consequences for people. Understanding this connection encouraged viewing science as an activity with moral aspects. Forming approaches to responsibility included discussion of the consequences of ideas and methods of their implementation. Such an ethic was not a set of ready-made rules. It represented a practical skill of comparing theoretical constructions with life realities. The organization of the day and the distribution of attention affected the depth of mental operations. Planning practices, habits of resting and switching tasks, and the ability to sustain creative fatigue became part of a thinker's arsenal. The combination of work and breaks helped maintain productivity and preserve clarity of thought. As a result, routine elements of life became not obstacles, but resources for sustained creative labor. The search for an intellectual community and the willingness to collaborate developed the ability to put ideas to the test. Communication with colleagues offered different points of view, broadened the notion of allowable arguments, and helped detect weak spots in constructions. Interaction relied on readiness to discuss and listen, which supported the maturity of argumentation. A network of such contacts became a platform for exchanging ideas and jointly developing more precise formulations. Early dispositions toward dedication formed an attitude to learning as a continuous process in which the goal is the development of thinking tools rather than the accumulation of facts. Such a view implies a critical attitude toward formal assessments and the value of intrinsic motivation. Assimilating this motivation helps choose activities and problems that correspond to long-term development of understanding. In the end, a thinker's image is composed of a set of practices aimed at building durable cognitive skills. Finally, the early philosophical stance contained the belief in the human mind's ability to create an ordered description of the world that remains accessible to understanding. This belief supported work under conditions of uncertainty and stimulated a demand for coherence of ideas. Belief served not as dogma, but as a methodological orienting principle that sustained the effort to seek simple yet powerful foundations for explaining phenomena. Such an attitude forms an approach to science as a collective labor of creating meanings that are open to verification and practical application. Einstein's thought experiments functioned as a laboratory for the mind, where intuition could be quickly tested, key assumptions isolated, and the voice of possible consequences heard. A scenario formulated in the imagination served as a reasoning tool that freed thought from the burden of calculations in order to isolate the essential. This method allowed one to condense a problem to its logical core and see which propositions require explicit formulation. This is the practical value of a thought experiment. It helps reveal which elements of a description are essential and which are distracting. The mind's work with simple images reproduced the act of modeling in an abbreviated form. The internal representation of a physical situation became a means of investigating relations between concepts. A strong imagination turned abstract requirements into tangible outlines available for analysis. At the same time, the image did not serve as final proof of truth, but helped pose questions for formalism. Visualization offered a chance to discern contradictions and gaps that formulas could mask, and formed a special kind of intuitive check applicable at early stages of thought. Economy of assumptions was a central practice in forming a thought experiment. A semantic victory was considered a situation in which a minimal number of assumptions generates a wide range of consequences. Such an approach made it possible to single out the universal characteristics of a phenomenon and assess the extent of its explanatory power. The principle of minimality provided a methodological scale. If the consequences turn out richer than expected, the chosen foundation possesses depth. If the consequences are narrow and local, the significance of the initial premises requires reconsideration. Working to reduce assumptions became a way to strengthen the generality of conclusions. Thought experiments functioned as a means of testing the concept of simultaneity and other fundamental categories. Through a simple mental construction, one could find out which propositions of language and physics prove to be interdependent. Describing the situation in the imagination revealed which terms need clarification, so that the reasoning retains meaning when the point of view changes. This is where the philosophical side of the method appears. Attention to semantics and to how formulation affects conclusions. Each imaginative trial demanded clarity in words, because unclear language produced illusory simplicity. The role of thought experiments concerned not only the production of ideas, but also tracking the limits of applicability of intuitive judgments. An imagined situation helped reveal places where intuition ceases to be a reliable halo and strict verification is required. Understanding this boundary-shaped methodological caution, images motivated further formal development rather than replaced it. Therefore, a thought experiment often opened the way to a mathematical reworking of an idea, which brought with it precision and the possibility of empirical testing. Mathematical language acted as the translator of imagistic thinking into a system of argumentation suitable for testing. Imagination suggested possible connections and symmetries, and mathematics gave them form and predictive power. This transition was the subject of constant attention. However convincing the image might seem, the true strength of an idea manifested in its formal interpretation. Consequently, the thought experiment created a demand for mathematical articulation, which in turn revealed additional conditions and clarifications that the image did not cover. The communicative function of thought experiments proved significant for publicly explaining complex ideas. A simple picture, placed in words, allowed the essence of the reasoning to be conveyed to the listener and to evoke intuitive understanding. Such a device performed a dual task. It helped the author smooth out internal complexities and at the same time exposed weak points of the argument that became apparent in the attempt to present the idea accessibly. The ability to hold a vivid scenario in mind helped build clear, illustrative explanations without loss of intellectual rigor. Epistemological responsibility accompanied every thought experiment. In creating an imagined situation, the thinker assessed how much it relied on commonly accepted observations and what new assumptions it introduced. Such an assessment served as a criterion for further development. If the imagined picture required excessive supposition, trust in its conclusions diminished. The principle of checking through observable consequences remained a constant guide, a reminder that the internal beauty of an idea is subject to external validation. Thought experiments cultivated a style of thinking oriented toward identifying invariant properties. Focusing on what remains constant under changing conditions offered a chance to find universal grounds for describing phenomena. The search for invariance became not merely a technical task, but a philosophical demand on the reliability of knowledge. At the same time, invariance was regarded as a criterion of explanatory depth. The broader the domain of applicability of a principle, the more it was perceived as fundamental. The creative role of imagination combined with discipline in formulation. An imagined setup stimulated novelty of ideas, and the requirement for precise formulation restrained thinking from arbitrariness. Such a combination produced productive tension. The freedom of imagination supplied material for hypotheses, and the discipline of formulation turned hypotheses into testable statements. Working in this mode developed the ability to see the difference between heuristics and proof, between a guiding idea and a claim awaiting confirmation. Thought experiments also served as an instrument for identifying the essential ethical responsibility in the actions of science. Considered consequences of an idea allowed one to estimate possible social outcomes even before their actual application. The analytical procedure of this kind required attention to how abstract principles might manifest in people's lives, and prompted evaluation of scientific goals with an eye to potential effects. In this sense, the method had a moral aspect. It encouraged foreseeing consequences and keeping criteria for the reasonable application of ideas. Interaction with colleagues enriched the quality of thought experiments. Discussion of images and scenarios served as a field for testing intuitions against others' intuitions. It was precisely in the clash of different imaginations that gaps and additional questions were discovered. Collective verbalization of a situation forced the formalization of the unspoken and clarification of assumptions, which made conclusions more robust and communicatively more reliable. The exchange of imagined setups became a way of collective growth in the method. Developing the skill of creating viable thought experiments requires practice and critical feedback. The ability to construct an imagistic scenario that is at once simple and filled with relevant details is formed through constant work on different problems. Training includes the ability to exclude insignificant elements, to focus on the main point, and to anticipate possible objections. Such a process produces a refined approach in which the image serves as a precise aid for further analysis. Contemporary scientific debates continue to demonstrate the fruitfulness of thought experiments. Questions about the nature of space, about fundamental symmetries, and about the limits of applicability of known theories often take their initial form in the researcher's imagination. The method has meanwhile been enriched. Now, mental constructions are quickly translated into mathematical models and subjected to computer testing. The very idea of searching for simple, powerful foundations retains its relevance, and the technique of mental modeling remains an important link in the chain of ideas from intuition to test. The final thought is connected to the fact that thought experiments point to a special link between economy of ideas and explanatory power. The work of the mind, concentrated on a minimum of assumptions and on clarity of formulation, acts as a way of building theoretical robustness. Imagination supplies the material, mathematics processes it, empiricism renders the verdict. The method itself remains valuable, not because it gives immediate answers, but because it frames questions in a form that makes them testable and comprehensible. The example of understanding space and time goes to the root of what is considered real, and the special theory of relativity offers a different vocabulary for talking about the world. The idea of space as a stage on which events unfold independently of the observer gives way to the thought of coordinates as parts of the language used to describe the same phenomenon. Such a reconstruction prompts reflection on the status of our descriptions. The question of what exactly exists beyond words becomes central. Widely used measurements turn out to be not merely convenient labels, but conditions of possibility for speaking about the facts of the world. Any experience has structure, and strict conditions of observation set that structure. In special conditions, where a signal is limited in speed, the concept of simultaneity ceases to be an unconditional criterion for placing events in the world. As a result, new ways of assessing causality and sequence emerge. The idea that relations between events are to be measured through light signals and clocks changes the habitual sense of time. The notion of now loses universality and becomes a local experience. Synchronization acquires the status of a practical convention, with consequences for how knowledge is constructed. Mathematical invariants act here as supports for metaphysics. Where relative quantities depend on the frame of observation, invariance provides stability. An invariant four-dimensional space-time structure functions as a criterion of what can be regarded as a true characteristic of the world, rather than an effect of viewpoint. Attention to invariance forms a special scientific ethic. Trust those structures that remain unchanged when perspective changes. This approach sets a direction for the philosophy of nature, where analysis shifts towards searching for deep regularities rather than superficial descriptions. Transferring the idea of mass-energy equivalence into the philosophical field generates the thought of interchangeability of qualities that were previously considered different in their essence. The concept of mutual transmutation of measurable quantities prompts a revision of notions of a thing as an immutable piece of reality. Awareness that what is called mass can be measured through energy stimulates philosophical reflection on how we distinguish entities and which tools we consider adequate for their description. In everyday speech, this is felt as a shift in the boundaries of what is considered stable and constant. The epistemological impulse of the theory manifests itself in the demand for experimental testability. A concept must yield distinguishable consequences in experience, and this change gives philosophy of science an emphasis on predictive power. Scientific credibility in this key becomes not a static merit, but a procedure in which a theory must withstand new modes of observation. This view alters the attitude toward abstract constructions. The beauty of formulas remains a valued trait, but true strength is the ability to accord with facts. Rethinking time as a component of the measurement system affects ideas about freedom and responsibility. If future and past are arranged in a structure that depends on conditions of observation, then the notion of predeterminateness of events acquires a different hue. The question of whether there is a unique temporal line ceases to be purely technical. This gives rise to new ways of speaking about possibilities and about those decisions conventionally considered free. Philosophical reflection concerns not only the metaphysics of time, but also the grounds used for moral reasoning about the consequences of actions. The role of language in forming the scientific picture of the world becomes more evident. Descriptions and mathematical structures operate as tools for coordinating experience, and philosophy faces the task of distinguishing between map and territory. The language of science does not merely reflect the world, it creates the conditions under which the world becomes observable. This determines a particular form of responsibility. In choosing concepts and ways of measurement, one sets the frame for possible interpretations of reality. Awareness of this responsibility requires more careful attention to the notions that serve as the foundation for subsequent inferences. The transition from intuition to formalism within a theory shows how abstract principles gain predictive power through mathematical articulation. Intuitive considerations about the constancy of physical laws found concrete expression in mathematics with predictable consequences for observation. Such a transition serves as an example of the methodological link between imagination and rigorous testing. In the context of philosophy, this is an important lesson in how hypotheses acquire criteria of empirical significance and become part of evidential practice. The very notion of measurement requires philosophical clarification. Clocks, rulers, signals become elements of a theory only if their use is subject to testing and intersubjective consistency. Thus, the methodology of science relies on common agreement about methods that can be described and reproduced. This agreement forms a collective picture of reality, and philosophical attention shifts from individual experience to the norms of coordination that make communication about facts possible. In this sense, theory creates an institutional environment for productive research. Energy, as a measurable quantity, ceases to be an abstract category and becomes a criterion for evaluating processes. Understanding the connection between energetic changes and quantitative indicators opens a new image of causality, where transformation becomes the measure of events. This encourages the thought that fundamental categories of the philosophy of the world can have operational definitions by which they gain precision and testability. Such operationalization helps avoid empty speculation and moves the discussion into the domain of concepts accessible to empiricism. Understanding the limits of a theory also acquires philosophical significance. A theory offers a model that works under certain conditions and requires refinements when its domain of application expands. This fact prompts reflection on the criteria used to assess the universality of ideas. Philosophy gains a tool for discussing the boundaries of knowledge, not only in terms of what we know, but in terms of how we justifiably extend our representations. Such an approach fosters a culture of scientific caution, in which each claim is weighed against the possibility of experimental verification. When a theory absorbs principles for coordinating time and space, it changes the approach to objectivity. Objectivity appears as resilience to change of viewpoint and as the ability to yield consistent predictions for different observers. This leads to a reassessment of traditional criteria of truth in science. Truth acquires an empirical tint. It is measured by the quality of a model's agreement with the observed effects the model promises to explain. This turn strengthens the practical orientation of the philosophy of science. The etymological sense of the word theory is enriched by practical consequences. Theory ceases to be merely explanation and becomes an instrument for action in the world. This is evident in how predictions allow the design of experiments and technologies. Hence, the philosophical thought about the connection between knowledge and the ability to influence the course of things. Knowledge, articulated through mathematical structures, becomes a means of transformation, and this raises moral questions about how and for what purposes scientific understanding is used. Adhering to the principles of minimal postulativity turns out to be a methodological strategy with moral dimensions. Choosing those postulates that yield the maximum of consequences from a minimum of suppositions reflects a preference for clarity and economy of intellectual resources. Such a choice affects a style of thinking and which paths of inquiry are considered acceptable. In philosophical terms, this implies a commitment to principles that provide broad explanation at limited cost in additional assumptions. The constructive interrelation between formula and experience leads to reflection on how theory shapes what is important to observe. Theory directs experimenters' attention, indicating which phenomena are worth recording. This change of direction in perception, as it were, gives science the role of evangelist for new facts that become significant only in light of specific theoretical settings. The philosopher must watch how theory changes criteria of significance and what new questions thereby arise. Rethinking basic concepts contributes to the emergence of a new scientific practice in which the evaluation of ideas combines aesthetic, logical, and empirical grounds. The beauty of simplification, agreement with observation, and internal precision form a triangle of criteria by which a theory's strength is tested. Such a balance turns scientific activity into a moral enterprise, in which the choice of ideas carries consequences for the direction of research and for how society perceives the role of science. And finally, the impulse to constant testing of ideas leaves the philosophical task of permissible limits of theoretical claims. The ability to formulate predictions that can be observed and repeated becomes a criterion of maturity of a claim. This raises the question of how to think further when established structures yield contradictory results. Philosophy obtains a field for critical analysis of premises and for searching for new supports that will withstand the test of time and practice. Such a process preserves interest in fundamental questions and prompts constant renewal of understanding of the world. The principle of equivalence became for Einstein the thought that shifted emphasis from force as the primary cause to the manner of describing the field. The reason for this shift lies in an attempt to connect general observable effects with the minimal set of conceptual premises. This structure consists in the assertion of local indistinguishability of gravity from acceleration. The consequence manifests in the invitation to consider gravitational phenomena as a property of the geometry of spacetime. The boundaries of this approach are delimited by requirements of locality and the possibility of local neutralization of the field. The difference in Einstein's view appears in the endeavor to pose a fundamental idea accessible both to intuition and to mathematical form. The idea that freefall turns a local observation into a standard of tranquility carries philosophical weight. The reason is that this changes the status of the object of investigation. Gravity ceases to be a property of matter and acquires the role of a condition of description. The structure of this thought rests on the mental separation between local experience and the global structure of the world. The consequences are a modification of notions of causality at scales beyond immediate experience. The limitations appear in the impossibility of locally eliminating global fluctuations or topological features. The difference in Einstein's method is expressed through attention to how local conventions form global requirements for the theory. Geometrization of the field brings to the fore the concept of the metric as the bearer of physical meaning. The reason for such reassessment is that measurements of distances and intervals are linked to the behavior of bodies and light rays. The structure consists in the formulation of metric properties through equations that set the interaction of matter and geometry. The consequence is a redistribution of ontological weight between objects and space. The boundaries of such an ontology are connected with mathematical complexities and the choice of coordinate systems. The difference in Einstein's approach is felt in the readiness to regard space as an active participant in processes. The locality of the principle creates a certain sense of intellectual modesty. The reason for this is that the assertion of equality of acceleration and gravity operates only in the neighborhood of a point. The structure of the idea presumes a method of local elimination of field effects. The consequence is a requirement of caution when extending conclusions to large scales. The boundaries here express the necessity of other principles when moving to cosmological problems. The author's difference manifests in respect for scale as a factor determining the applicability of general claims. The understanding of causality in a space where geometry participates in dynamics leads to new ethical and methodological questions. The reason for these questions is that the predictive power of a theory is tied to the choice of principles. The way these choices are organized influences the direction of research and the allocation of resources, and the consequence is responsibility for methodological commitments. The boundaries of that responsibility concern the technical and social consequences of applications, and Einstein's difference is apparent in how he combined pure theory with concern for its consequences. The equivalence principle functions as a test of the completeness of the description of the world. The reason for such a test lies in the contradictions between the local and global characteristics of the field. The mechanism of checking envisages comparing local measurements with the mathematical structure of geometry. The consequence becomes the necessity of experimental verification of formulations. The limits of this verification are set by instrument precision and the innate limits of observability. Einstein's difference in style of inquiry manifested in his insistence on the clarity of physical meanings. The connection between the principle and the idea of general covariance sets the tone for the philosophical understanding of objectivity. The reason for trust in general covariance is the universality of formulations. Its mechanism is expressed through the requirement that equations be invariant under coordinate transformations. The consequence is a shift in the understanding of truth as the stability of formulas under changes of descriptive perspective. The boundaries show up in contentious issues of interpreting mathematical solutions. Einstein's difference reflects a tendency to look for deep criteria that withstand changes in the observer's point of view. The dynamics of the field, whose equations link curvature and the energy momentum, carry with them the philosophical idea of reciprocity between the conditions of existence and the activity of matter. The reason for this understanding is that the mathematics implies mutual influence of components. The mechanism of this exchange is expressed through a formula of feedback between matter and geometry. The consequence becomes the conception of the cosmos as a system of interdependent properties. The boundaries of the concept touch situations with singularities and extreme conditions. Einstein's views differed in his respect for the interconnectedness of phenomena as a key mark of reality. The equivalence principle requires a certain discipline in posing questions about what is observable. The reason for this discipline is that the interpretation of data depends on accepted local conventions. The mechanism of disciplining implies standardization of measurement and verification procedures. The consequence is a strengthening of the institutional side of science. The boundaries of institutionalization appear in hypotheses that demand different methodological approaches. Einstein's difference is felt in his effort to combine individual intuition with collective verifiability. The philosophy built around the principle comes into contact with the metaphysics of space. The reason for this contact is that the conception of the structure of the world determines how questions about being are formulated. The mechanism of the metaphysical approach relies on notions of space as an active element. The consequence is a restructuring of the ontological and epistemological basis. The boundaries of metaphysics are marked by the fact that mathematics leaves many interpretations open. Einstein's difference is seen in his readiness to translate mathematical images into philosophical vocabulary. The idea of the local equivalence of acceleration and gravity expands the notion of what counts as an observable fact. The reason for this expansion is that the conditions of observation themselves become elements of the theoretical description. The mechanism of this expansion is expressed in the inclusion of the instrument procedure within the structure of the theory. The consequence is the strengthening of the role of operational definitions. The limits of these definitions concern the ability of instruments to register subtle effects. The Einsteinian position differs in its attention to the instrumental component of knowledge. Perceiving space as a dynamic stage forces a rethinking of the idea of a stable foundation for scientific knowledge. The reason for this rethinking is that while the metric changes, former criteria of stability lose meaning. The design of a new foundation presupposes reliance on invariants and principles. The consequence is the demand for immutable structural characteristics. The boundaries of this demand are determined by mathematical and physical constraints. Einstein's difference is noticeable in how he valued the robustness of forms rather than the ornamentation of descriptions. The equivalence principle has an aesthetic dimension in scientific choice. The reason for the aesthetic feeling is the simplicity and depth of the idea. The mechanism of aesthetics manifests through the consonance of intuition and formalism. The consequence is a tendency for researchers to turn to principles that possess clear visual and logical imagery. The boundaries of aesthetics are visible where apparent simplicity deceives and leads to erroneous generalizations. Einstein's difference is striking in that he regarded aesthetic criteria as a substantial argument when choosing theoretical directions. The general theory born from the principle changes the role of the observer in the structure of the world. The reason for this change is that the observer is found to be embedded in the dynamics of the space-time structure. The mechanism of this embeddedness is expressed through the dependence of measurements on trajectories and states of motion. The consequence is a revision of the traditional picture of a detached subject. The boundaries of the revision concern questions of subjectivity and intersubjective agreement. Einstein's philosophical approach differed in that he considered it important to preserve criteria of objectivity, adapting them to new conditions. The limits of the equivalence principle open the way to philosophical problems of the future. The reason for this opening is that local equivalence does not answer questions about the quantum structure of space. The mechanism of future questions presupposes a combination of principles of general relevance and microscopic postulates. The consequence will be the necessity to revise basic concepts of ontology and epistemology. The boundaries of possibilities point to techniques and language that are yet to be developed. Einstein's difference was that he asked questions that directed generations toward their resolution. Reflections on the equivalence principle lead to a reassessment of scientific responsibility in a broad sense. The reason for the reassessment is the theory shapes ideas of what is possible and permissible. The mechanism of responsibility is expressed through requirements for communicating ideas and transparency of argumentation. The consequence is increased public attention to scientific policy. The boundaries of responsibility touch upon moral dilemmas in the implementation of new technologies. Einstein's difference manifested in openly discussing such dilemmas and in a persistent search for moral benchmarks. Rethinking causality within a geometric theory creates a field for new philosophical ways of asking questions about free will and determinism. The reason for the reassessment is that the structure of the world influences the available trajectories of events. The mechanism of analysis includes consideration of possibilities and constraints. The consequences are a vision of standard models of predictability. The boundaries of the application of these models are determined by context and scale. Einstein's difference was that he saw freedom in the context of structural possibilities, not as an absolute attribute of an agent. The philosophical legacy of the equivalence principle remains provocative. The reason for the provocation is that it offers a new vocabulary for conversations about reality. The mechanism of this legacy consists in pushing thinkers to revise basic categories. The consequence is a constant demand for the clarification and testing of earlier ideas. The boundaries of the legacy are visible in the history of science, where outdated metaphors are replaced by new ones. Einstein's difference lies in that he provided an instrument that continues to pose questions and demand answers in a wide variety of contexts. The reason is that physical intuitions required a language capable of expressing subtle relations between measurements and processes. The mechanism of this language turned out to be in mathematical constructions that pushed toward a system of representations of the world. The consequence was that mathematics became simultaneously a tool and a criterion of truth. The limits of that role were determined by the level of abstraction the scientific community was prepared to accept. Einstein's difference manifested in that he always regarded mathematical formulas as a means to translate an imagistic sense into strict speech, not as an end in themselves. Einstein's mathematical imagination arose from simple mental schemes, and the mechanism of this practice consisted in seeking minimal expressions capable of accommodating a wide spectrum of phenomena. The consequence was the birth of equations that read like geometric characteristics of the world. The limits of the method were marked by the necessity of rigorous testing and clarification of the symbolism. Einstein's difference was expressed in tolerance for tentative formulas and in his readiness to invite those with technical training to bring them to formal rigor. The reason for turning to geometry lay in the need to make sense of measurements and light signals as primary elements of experience. The mechanism of the solution consisted in drawing on Riemann's work and then in transferring ideas about the metric into a physical substrate. The consequence was a change in attitude toward the very idea of space. The boundaries of the approach concerned understanding which mathematical postulates could be considered physically interpretable. Einstein's difference consisted in the ability to show how abstract geometry acquires empirical significance through concrete physical processes. The reason for seeking help from geometers arose when intuition required technical completion. The mechanism of collaboration was built on personal meetings, exchanges of letters, and mutual explanation of problems. The consequence was the formalization of theories into stable mathematical structures. The boundaries of such interaction manifested in differences of professional language and methodological habits. Einstein's difference showed in his respect for the other's rigor and in the ability to formulate physical problems so that they became interesting to pure mathematicians. Mathematics served as a filter for aesthetic preferences. The reason for this is that symmetry and simplicity worked as orthodox criteria for choosing rules. The mechanism of aesthetic selection was expressed through a tendency to follow principles of invariance and parsimony of postulates. The consequence was concentration of effort on equations with clear geometric interpretation. The boundaries of aesthetics were defined by the possibility of error when excessive trust is placed in beauty. Einstein's difference manifested in that he allowed the aesthetic criterion, but always sought contact with observable content. The reason for difficulties in the reception of complex mathematical ideas by the physics community lay in the separation of disciplinary languages. The mechanism of the solution included building bridges through lectures, letters, and joint publications. The consequence was the gradual integration of new methods into physical practice. The boundaries of this process depended on educational institutions and cultural barriers. Einstein's difference was expressed in a persistent striving for clarity when conveying abstract thoughts, and in readiness to dialogue with those who have different training. Mathematical requirements imposed constraints on possible physical theories. The reason is that analytical coherence and symmetry acted as natural filters. The mechanism of such selection consisted in using principles of covariance and invariance. The consequence was a narrowing of possible forms of equations and an increase in predictive power. The boundaries of the method appeared when attempting to describe phenomena where classical mathematical tools give weak guidance. Einstein's difference was that he saw mathematical constraints not as a barrier, but as a guide for intuition. The reason for the transformation of mathematical images into ontological assertions appears when formulas become sources of metaphysical conclusions. The mechanism of this transformation consists in ascribing reality to those elements of a theory that play a key role in the equations. The consequence is a rethinking of space and matter as interdependent categories. The limits of such ontological steps are set by empirical control and interpretational flexibility. Einstein's difference lay in caution when drawing conclusions about reality, and in leaving room for experimental correction of metaphysics. The reason why mathematical modeling required simplifications lay in the need to obtain applicable predictions. The mechanism of these simplifications was reflected in methods of linear approximation and small quantity perturbation. The consequence was the possibility of comparing theory with observations in concrete experiments. The limits of approximations became apparent under extreme conditions where linear idealizations break down. Einstein's difference showed in that he took the results of approximations into account, but retained the strive for a more general and rigorous formulation. The reason for dialogue with geometers was the search for rigorous mathematical proofs of intuitive considerations. The mechanism of such conversations looked like an exchange of problems and mutual correction of terms. The consequence was formal justification for previously heuristic ideas. The boundaries of joint work were determined by how well physical problems fit into purely mathematical frameworks. Einstein's difference manifested in the ability to bring a problematic situation from physics into mathematical language without losing its intuitive direction. Mathematical sophistication generated the need to train a new kind of specialist. The reason for this is that traditional courses provided limited depth in topology and differential geometry. The mechanism of educational transformation included introduction of specialized courses, seminars, and individual consultations. The consequence was the emergence of a generation of scholars capable of thinking at the intersection of disciplines. The boundaries of educational reform were determined by resources and academic traditions. Einstein's difference was that he personally invested in teaching colleagues and students, explaining complex things with simple images. The reason that mathematical ideas influence popular understanding of science is their ability to provide concise and expressive metaphors. The mechanism of this transmission is the translation of technical concepts into figurative descriptions. The consequence is the spread of interest in fundamental questions to a broad audience. The boundaries of such translation are linked to the possibility of oversimplification that leads to distortions of the essence. Einstein's difference manifested in that he conversed in the language of physics and in the language of accessible images in parallel. Mathematics in experiments serves not only as a tool for calculation. The reason is that the structural demands of formulas shape the expected features of phenomena. The mechanism of this connection is that equations indicate which quantities should be measured. The consequence is the direction of experimental practice. The limits of such influence are determined by the capabilities of instruments and the interpretational clarity of data. Einstein's difference lay in his insistence that mathematical recommendations be accompanied by clear indications of observable content. The reason Einstein's legacy produced new branches of mathematics and physics is that his equations opened unexplored regions. The mechanism of their influence is expressed in the formation of entire disciplines devoted to global properties of space and gravitation. The consequence is a strengthening of the link between abstract research and engineering applications. The limits of this link manifest in unsolved problems where existing methods prove insufficient. Einstein's difference consists in the gift of formulating problems that continue to serve as a guide for subsequent generations. The significance of experimental verification for Einstein grew out of the demand for an interpretive anchor for abstract formulas. The reason for that demand was that equations can provide aesthetic satisfaction, but without connection to the observable world, they remain unsubstantiated assertions. He organized testing by carefully transforming abstract predictions into concrete, measurable signatures, specifying sets of physical quantities and conditions under which differences between hypotheses would become visible. As a result, the theory gained not only mathematical coherence, but also practical testability, which made it historically significant. The limits of this strategy showed where instrumentation was weak or observable effects were extremely small. Such cases required patience and gradual accumulation of data, as well as technological development. Einstein's difference consisted in the requirement for clarity about what exactly was being measured and in persistence in making predictions as concrete as possible, so that experiment could decide the matter. The structure of the equations themselves indicated which parameters deserved attention, and this indication was the reason for the formation of experimental programs. The mathematical form suggested where to look for anomalies and which dependencies should be checked. The mechanism of this translation included constructing suitable measurement tasks and proposing criteria of correspondence between data and theoretical quantities, often through recommended experimental configurations or averaging methods. The consequence was the concentration of resources on experiments capable of distinguishing traditional views from new predictions, which sped the incorporation of ideas into the stable scientific corpus. The limits of the method were signaled by the theoretical dependence of some measurements. The definition of a quantity generated dependence on the chosen model, and neutralizing that dependence required additional independent checks. Einstein's uniqueness showed in his demand to bring mathematical objects to operational definitions that could be implemented directly in the laboratory or observations. Thought experiments served as a technical mechanism for translating intuition into testable claims and were prompted by the need to check the meaning of key concepts without immediate recourse to instruments. Constructions in the imagination allowed one to draw qualitative consequences of a theory and to propose summaries of which effects should be expected when conditions change. This made it possible to form hypotheses suitable for practical realization and facilitated understanding of which parameters needed to be controlled in tests. The limits of this practice arose when mental scenarios gave false impressions of the real behavior of complex systems. Overcoming them required empirical testing and a readiness to modify imaginative setups. Einstein's peculiarity lay in combining intensive use of mental constructions with the requirement of their subsequent empirical verification. For him, thought served as an instruction to action, not as a substitute for observation. The demand for novelty in predictions was born from the need to put a theory at risk and give it the chance to fail if it was wrong. The reason for this attitude was that only a system exposed to risk receives maximally informative feedback. The mechanism of this approach looked like an effort to identify consequences that would differ from already accepted theories, and to measure precisely those parameters where divergence was expected. As a result, the scientific community could judge the viability of a new idea by the field of experimental data and statistical criteria. The limits of the approach depended on the size of the effect and measurement precision. Small deviations could remain hidden for a long time, which required patience and consistency in experimental campaigns. Einstein stood out in that he deliberately demanded bold, risky predictions, understanding that they give a powerful contribution to the epistemic value of a theory. Appeals to anomalies arose because each data point that failed to conform to expectations reported a discrepancy between the model and reality. The mechanism for dealing with anomalies included a critical re-examination of assumptions and the translation of contested observations into comprehensible terms. The consequence of such practice was either a refinement of the theoretical picture or an indication of the need for new physical principles. The limits of this strategy appeared where an anomaly could be the result of systematic errors or incorrect interpretations, which required caution in conclusions and replication. Einstein's difference in approach manifested in a readiness to take discrepancies seriously and in a demand to seek root causes, which made his responses to anomalies productive rather than merely reactive. The role of instruments and verification technology was prompted by the limitations of human senses and the need for external registration of small effects. The structure of the interaction between science and engineering involved formulating target quantities and designing devices to record them. The consequence of this interaction was an interdependence between theoretical demands and the development of instruments, where theory motivated technical innovation, and new capabilities opened access to experiments of previously unattainable scales. The boundaries of such interaction were determined by resources, cost and time constraints, as well as considerations about acceptable device complexities. A distinctive feature shown by Einstein was respect for the role of experimenters and the willingness to adopt theoretical formulations to realistic measurement capabilities. The connection between mathematical structure and the choice of what to measure emerged because formulas imposed priority on certain combinations of quantities. The arrangement of this connection consisted of analyzing symmetries and invariants that pointed to observable constants or relations. As a result, experiments acquired a purposeful structure that facilitated the identification of features matching theory with reality. The limits of such navigation were evident when chosen parameters were sensitive to additional, unforeseen factors and required extra control. Einstein was notable for his ability to interpret symmetries not as a purely mathematical trick, but as guidance as to which experimental evidence has fundamental significance. Reflections on light and time arose from the need to specify the concept of simultaneity and to assess the practical operational procedure for establishing it. The procedure of this work consisted in detailing synchronization protocols and in translating abstract concepts into practical measurement methods. The consequence was a rethinking of temporal coordinates and proposed ways to test the transportability of light signals as a standard. The limits of such rethinking were marked by situations in which synchronization standards could conflict or be ambiguous in gravitational fields and accelerated systems. A distinctive trait of Einstein was his emphasis on the practice of defining concepts rather than on metaphysical constructions. For him, the concept of time and space obtained clear operational bases. Statements about the relation between energy and mass appeared as theoretical claims that required empirical interpretation, because their meaning was lost without specifying the context of conversion. The mechanism of verification consisted in identifying processes where the proposed conversion would yield measurable products or a mass deficit. As a result, the theory acquired an applied dimension and served as a guide for designing experiments and evaluating their outcomes. The boundaries of testability were expressed in the need for high energies or precise methods that were not always immediately available. Einstein differed in that he treated such relations as deep structural links, but insisted on a cautious and transparent path from formula to experimental demonstration.
Reactions to negative results arose from recognition of the informational value of an absence of effect. The mechanism of such reaction consisted in strengthening control criteria and checking alternative error sources. The consequence was refinement of theoretical frameworks and sometimes abandonment of former hypotheses if negative data were confirmed repeatedly. The limits included the risk of premature rejection of fruitful ideas due to limited data or flawed methodologies. Einstein showed respect for negative results as a source of knowledge that allowed narrowing the range of acceptable models, while demanding careful verification of methods before revising core assumptions. The statistical character of many experiments implied the need to formalize expected distributions and significance criteria. The reason being that single measurements rarely carry sufficient information. The procedure for working with statistics included the development of averaging methods, error estimation, and the presentation of confidence intervals. As a result, an objective way of relating theory and practice emerged, where probability served as a means of evaluative certainty. The limits of the approach were visible in the interpretation of statistical results and in the possibility that different theoretical models could give similar statistical predictions. Einstein emphasized the necessity of a clear understanding of what exactly a model predicts, and he persistently sought ways to reduce vague statistical statements to concrete, fundamentally testable facts. The social side of verification manifested because scientific conclusions require collective trust and reproducibility, and the mechanism of this process relied on publications, cross-checks, and replications. The consequence was the formalization of procedures by which results became accepted through repeated verification and critical discussion. The boundaries of this mechanism were expressed in social and institutional factors capable of slowing the adoption of innovations, or, conversely, accelerating fashions in hypotheses. Einstein's approach differed in his ability to formulate his ideas so that they were open to criticism, while engaging in dialogue with experimenters and promoting procedural transparency. The ethical dimension of experimental practice arose from the awareness that some predictions have significant consequences for society, and the structure of responsible behavior required assessment of consequences already at the stage of formulation. The consequence of this thinking was caution in public statements and in recommendations for the use of scientific achievements. The limits of responsibility were determined by the complexity of forecasts and the extent of control researchers have over the application of results. In this regard, Einstein's distinctiveness manifested in his sense of moral responsibility as a scientist, in a willingness to weigh the potential of knowledge and its possible impact on the world.
Selection of experimental programs by the criterion of discriminative power arose from the practical need to spend resources efficiently, and the structure of this selection consisted in prioritizing those experiments that could rule out a wide class of alternatives. The consequence was faster progress toward truth and the release of resources for the most informative tests. The limits of such selection were the risk of missing important but hard-to-reach effects if their prospects were misjudged.
Einstein differed in that he preferred to bet on experiments that resolved philosophical questions about the structure of the world, not only on technically simple measurements. The pedagogical aspect of an experimental orientation arose from the task of conveying complex ideas to students through demonstration of concrete consequences, and the mechanism of this transmission included the use of simple protocols and illustrative examples. The consequence was better assimilation of fundamental concepts by succeeding generations of researchers. The limits of this technique involved the risk of oversimplification, which could distort deep semantic connections. Quantum mechanics provoked deep philosophical unease in Einstein because its statistical form of statements conflicted with the demand for a complete description of the world. The reason for this unease lay in the conception of the scientific picture as a means to give an exhaustive answer to the question of what reality is. The tool of his reflections became conceptual counterexamples and carefully chosen arguments aimed at clarifying which elements of reality are regarded as physically significant in the theory. As a result of ensuing discussions, the notion of completeness was brought onto the stage of philosophical analysis and gave rise to a whole body of work that challenged the readiness to accept probability as the final characterization of nature. The limits of this line of criticism appeared in the difficulty of translating philosophical criteria into strict empirical tests, since some assumptions about locality and the independence of preparation conditions required separate verification.
Einstein's difference in approach manifested in that he demanded from a theory not merely utilitarian predictions, but claims to represent properties of the world existing independently. And it was this demand that shaped the direction of his critical questions. The striving for deterministic explanation served for Einstein as a philosophical orienting principle, because an order of causes and effects provided him with a criterion of what counts as a satisfactory theory. The reason for such orientation lay in the conviction that the meaning of randomness should be explainable through deeper laws. As a working method, he proposed to regard probabilistic statements as reflecting the incompleteness of our knowledge, and as a signal of the existence of additional variables or structures not yet described. The consequence of this view was the emergence in the philosophy of science of projects seeking alternative formulations of quantum mechanics, and a revived interest in hidden variables and ontological models. The limits of this approach became apparent with the development of theorems that established strict constraints on the possibilities of combining locality with classical type hidden variables, thereby casting the problem in a different light. The rigor of Einstein's thought experiment method contrasted with an intuitive readiness to tolerate fundamental randomness. He sought general principles capable of explaining probabilistic results as consequences of a deeper structure.
The question on the role of the observer acquired practical importance for Einstein, because replacing the description of the world with a procedure of measurement shifted philosophical responsibility from theory to the act of observation. The reason for this concern was that such a substitution diminished the aim of presenting the world as existing independently of our interventions. For his analysis, he used clarification of operations and the requirement that the concepts underlying a theory have clear operational definitions, suitable for discussion outside a specific measurement context. Consequently, the discussion of the wave function moved from a technical formula to questions about the status of theoretical entities and about which interpretation provides a genuine picture of reality.
The limits of this emphasis showed that some contemporary interpretations proved successful in practical terms, offering working models that did not attempt to satisfy all metaphysical demands. Einstein's uniqueness lay in insisting on separating the epistemic level related to knowledge from the ontological level related to existence. The completeness criterion he proposed in the formulation about elements of reality arose as an attempt to bring philosophical intuition into formal rhetoric. The reason for this step was the need for an instrument that would translate general demands on a theory into clear conditions of comparability. The construction of the criterion was based on the notion of predictability with complete knowledge of conditions and on the assertion that if one can predict the value of a quantity with complete certainty, then the corresponding quantity must exist as an element of reality. The consequence was a complication of the discussion about what counts as a proof of completeness and which empirical combinations of approaches are relevant. The limits of this criterion met paradoxes arising when accounting for correlations of distant systems, where assumptions about independence could prove questionable. Einstein differed in that he proposed not a purely philosophical hypothesis, but a measurable test aimed at clarifying the relation between predictability and reality. The problem of locality acquired for him ethical and methodological significance, because recognition of the instantaneous influence of some events on others required the revision of the basic postulates he considered the background of any rational physics. The reason for advancing such a demand was respect for the principles developed in the theory of relativity. Methodologically, he relied on strict formulations about the impossibility of transmitting signals faster than light, and on logical deductions about the consequences of asserting connected states. As a result of the discussion, it became clear that the question of locality was closely linked to the choice of ontological and epistemic assumptions, and further theoretical developments led to the emergence of precise mathematical criteria testable in experiments. The limits of this line of argumentation showed that any attempt to restore a deterministic picture must take into account results that limit the compatibility of locality and realism. Einstein's steadfastness is evident in his effort to preserve the compatibility of fundamental principles, even when this required revising customary methods. His methodological attitude toward the tools of thought demonstrated a unique mixture of criticalness and constructiveness, because he held that philosophical complaints should be supported by proposals to replace or rework the theoretical apparatus. The reason for this practice was the conviction that scientific philosophy is obliged to accompany experimental and mathematical efforts with concrete alternatives. As a structure of discussion, he supposed that talk about the nature of theory should include the proposal of models that allow comparison of expected consequences and thereby reveal differences at the level of observations. The result was a productive environment where philosophical theses were enriched with technical empirical content rather than remaining pure abstractions. The limits of this position appeared in the fact that there were not always available experimental methods to carry out the proposed tests, which required patience and investment in technology. A feature of Einstein's approach was that philosophy for him was never an end in itself, but always served as a tool for improving scientific understanding. The attitude toward probability as an epistemic phenomenon was built on the calm conviction that randomness indicates a gap in description, rather than a declaration of a fundamental property of being. The reason for such an interpretation lay in the search for causal structure capable of explaining distributions. For the analysis of this attitude, he used the notion of ensemble and examples from statistics where distributions arise from known dispersion of initial conditions. The consequence was the development of approaches that interpret quantum statistics as an instrument for predicting statistical regularities, not as a direct report of the unpredictability of individual events.
The limits of these approaches were found in cases of contextual dependence of measurements and in logical theorems showing the impossibility of a certain type of reduction of probability to mere ignorance. Einstein's difference consisted in considering probabilistic descriptions as a temporary measure of incompleteness rather than the final answer. The philosophical impact of his critique manifested itself in a broad and long-lasting influence on the minds of philosophers and physicists, because the questions he raised proved methodologically fruitful. The reason for this impact lay in the persistent formulation of problems that concerned the very structure of scientific knowledge. The mechanism of influence consisted of epistolary and public texts, in which he set out his objections in a clear form and proposed concrete directions for research. As a result, the debate around quantum mechanics acquired the long-term character, spawning many interpretative directions and stimulating the development of formal results. The limits of this influence showed that philosophical demands can be sidelined under pressure from practical effectiveness of a theory, and that the priorities of the scientific community can shift according to applied successes. Einstein differed in that his philosophical activity sprang from an internal scientific motivation and a desire to improve the toolkit of physics, not from external criticism. The ethical dimension of his critique manifested in caution when advancing claims capable of directing research programs, because acknowledging incompleteness or the need for a new theory mobilizes the resources and attention of the community. The reason for this caution lay in responsibility for how philosophical theses are realized in practice. For practical implementation of this approach, he pointed to the importance of clear criteria for evaluating alternatives and to the significance of proposing testable consequences. The consequence of this manner was that disputes about fundamental concepts were accompanied by plans for their empirical verification rather than remaining verbal disputes. The limits of this approach appeared in the possibility of mistaken prioritization, when the direction of efforts may prove less productive than expected. Einstein's distinction was expressed in combining philosophical exactingness with a drive to plan experimental strategies. Reading his thoughts on quantum mechanics today serves as a source of cautious optimism, because many problematic points he indicated continue to be the subject of active research and offer new opportunities for understanding. The reason for the sustained relevance is that questions about completeness, locality, and the meaning of probability remain cornerstones of modern science. In practice, this is expressed in the fact that contemporary research uses quantum information approaches and experimental protocols to test the very principles that were the subject of earlier debates. As a result, it becomes possible to rethink classical intuitions and simultaneously to transform philosophical questions into technical tasks suitable for testing. The boundaries of such rethinking are determined by the emergence of new theoretical results that require flexibility in interpretations and a readiness to revise earlier views. The most remarkable thing about Einstein's legacy is that he showed how philosophical demands for clarity and completeness can coexist with scientific practice and provide fruitful directions for the development of physics. His ability to convey the complex beyond the scientific community grew out of the conviction that ideas matter not only within laboratories and formulas, but also in the public imagination. The reason for this conviction was that a theory without public reflection becomes an instrument without moral assessment. The structure of this ability was built on simple images that preserved the logical structure of the argument, while making it accessible to those who did not master the technical language. The consequence of such a manner of communication was the dissemination of scientific problems into the sphere of political and philosophical discourse, which changed the subject matter of discussion
and broadened the circle of those who could participate in decision-making. The limits of this approach revealed themselves when simplicity turned into a loss of precision, and when image replaced argument. His distinction lay in that he strove to preserve intellectual honesty in simplification, demanding clarity from popular writings without slipping into sloganizing. He translated mathematical constructions into visual schemes that acted as a bridge between abstraction and intuition. The reason for this practice lay in the desire to make fundamental propositions testable, not only in terms of calculations, but also in terms of common sense.
The apparatus of translation relied on a series of successive images, each of which led the listener to a critical question about the structure of the world. The consequence was the formation among a broad audience of the impression that science is accessible and comprehensible, and that its claims withstand logical scrutiny in the mind of each person. The limits of the method were revealed in the public's tendency to take the metaphor for a final conclusion, and in the possibility of losing nuances that require mathematical apparatus for clarification. His difference consisted in the insistence on keeping the public within the field of philosophical inquiry, rather than in the role of passive consumer of images. The voice in his public texts combined the lightness of style with a demand for argumentation, because he understood that trust is built through clarity and honesty. The reason for this strategy was the desire to avoid the demonization of science, while simultaneously preserving its autonomy as a way of knowing. The rhetorical arrangement included the use of examples drawn from common experience and direct questions that forced the listener to relate abstract propositions to moral intentions. The consequence was the formation of the image of a scientist, ready for dialogue and capable of taking on intellectual responsibility. The limits of this manner manifested when the symbolism of personality began to eclipse the arguments, turning discussion into a manifestation of faith in authority rather than a testing of reasons. The distinction lies in that, for him, publicity was a tool of clarification, not self-promotion.
His texts for a wide audience functioned as exercises in the philosophy of science, since they set criteria for trust in theories and raised questions about the ends of knowledge. The reason for this functioning was linked to the conviction that the shaping of public opinion about science should be based on clear notions of method and values. The structure of such texts combined analytical dissections with moral reflections, which allowed the reader to relate a scientific claim to its consequences for society. The consequence was broad involvement of the intellectual community in discussing technological and political questions, which required a baseline of scientific literacy from the public. The limits of such intervention were revealed when technical details required expert scrutiny and when public dialogue encountered conflicting interests. His difference manifested in the constant reminder that science has a value-laden aspect that cannot be ignored. The image of the scientist in public memory was created through a combination of words and visual symbols, since photograph and quotation cemented perceptions of rationality and empathy. The reason for using such a combination lay in the awareness that human perception operates with images that effectively convey complex ideas. The construction of the image included recurring motifs of modesty and wonder before the world, which made scientific activity attractive and comprehensible. The consequence was increased public support for science as a cultural phenomenon, and the transfer of respect for methods of critical thinking into a broader sphere. The limits of the image manifested in the tendency to reduce attention to the individual, thereby diminishing visibility of the collective nature of scientific labor.
The distinction consisted in that he used the image not for fame, but for the possibility of conducting a serious conversation about values. He viewed the interaction of the scientific and political spheres through the prism of responsibility for the consequences of applying knowledge. The reason for this approach was the sense of moral obligation that arises with the growth of technological power. The positioning structure included statements about society's right to be informed and about the duty of scientists to participate in public discussion when it concerned fateful decisions. The consequence was the activation of ethical debates around the development and use of new technologies, as well as the involvement of the scientific community in discussions of regulation and international agreements. The limits of this approach arose from the fact that politics has its own logic of interests, and that scientific arguments are not always decisive in the allocation of power and resources. The distinction manifested in a willingness to take on the role of intermediary between knowledge and morality. One specific historical situation revealed the complexity of moral responsibility, because a choice made under conditions of danger required the combination of foresight and humility before the incompleteness of knowledge. The reason for the complexity lay in the fact that technological capabilities can appear before a public consensus on the rules for their application is formed. The structure of the dilemma implied analysis of possible consequences, negotiations with authorities, and subsequent public articulation of scientists' positions. The consequence was an increased moral burden on knowledge bearers and heightened expectations for the scientific community's participation in governmental decisions. The limits of such intervention consisted in the risk of erroneous assessment of prospects and in the inability to foresee all side effects of implementing technologies. The distinctiveness of his approach was that he considered it necessary to combine warning with work on risk mitigation. Statements on political matters fit into a broader conception of universal humanism, since reflections on justice and peace were not an external add-on to scientific activity, but its moral background. The reason for this interrelation lay in the conviction of the close interdependence of knowledge and the conditions of human well-being. The arrangement of public speeches included appeals to universal human values, to international institutions, and to ideas of legal responsibility. The consequence of these statements was the mobilization of opinion and the creation of platforms for transnational dialogue about the risks of science. The limits of political activity were found in the limited influence of a single voice on the realities of international politics, and in the possibility that political effectiveness is incompatible with scientific neutrality. The distinctive aspect of the approach was the effort to link scientific autonomy with moral obligation. The idea that enlightening society is part of the scientific mission underpinned his demands for education and for discussing values in schools and universities. The reason for this was that the public's capacity for critical thinking affects the quality of political decisions and society's readiness for technological change. The structure of such demands included support for scientific literacy, participation in public lectures, and the creation of accessible texts that explain the connections between theories and the consequences of their practical applications. The consequence was the gradual strengthening of education's role in forming civic responsibility and improving conditions for measured discussions about science in society. The limits of these efforts manifested in social inequality and in the varying readiness of communities to receive complex nuances. The distinction lay in the persistent presentation of science as a public good. He regarded the difference between scientific authority and moral authority as the subject of separate analysis, because success in one realm did not guarantee competence in the other. The reason for this demarcation was evident when discussing political decisions, where moral evaluations go beyond technical expertise.
The structure of the demarcation required honest statements about the limits of one's knowledge and the active involvement of various social groups in discussing value questions. The consequence of this approach could be the strengthening of trust based on transparency and readiness for collective choice. The limits of the approach were noticed when public expectations required from the scientist more than he could provide, and when public figures became drawn into disputes far removed from scientific methods. The distinction in his approach manifested in the scientist's desire to participate in moral discussions without claiming omnipotence in resolving all issues. The public role he assumed also functioned as a model for future generations of scientists, because it demonstrated a combination of professional rigor and civic responsibility. The reason for such modeling was that science develops within society, and its prospects are determined both by the scientific community and by social conditions. The mechanism for transmitting the model included mentorship, public lectures, and examples of personal behavior that became topics of discussion in educational institutions. The consequence was the formation of expectations that a scientist should be not only a specialist, but an active participant in public life. The limits of such expectations lay in the risk of idealizing the role and in the inability of individuals to meet universal standards. The distinctiveness of the approach was a sincere readiness to share the burden of responsibility. Reading his public texts today is useful as an example of how thought can combine clarity and responsibility, for they show that explaining scientific knowledge and discussing its consequences form a single field. The reason these texts remain relevant is that the present faces similar dilemmas, where the speed of technological change outpaces normative mechanisms. The way of applying his legacy to the present implies developing institutions capable of engaging experts in society in the joint assessment of risks. The consequence of such application may be a more measured policy in areas where science and technology have serious ethical implications. The limits of such efforts are visible in the difficulty of international agreement and in the multiplicity of interests. The distinctiveness of his example is that he showed how personal honesty of thought and public readiness for responsibility can raise the quality of public dialogue. This ability to raise the quality of public dialogue proved to be the result of a combination of three components: rigor of thought, clarity of language, and willingness to answer for the consequences of one's ideas. The conviction that theories matter not only for calculations gave rise to a practice of explanation built as a successive argument, reducible to comprehensible images and testable consequences. This way of organizing explanation involved sequential steps from a general premise to its empirical consequences, with a constant consideration of the moral context of applying the conclusions. The consequence was the social institutionalization of demand for scientific responsibility and the emergence of the expectation that scientific claims should be accountable to civic reflection. The limits of this practice appear when an image becomes a substitute for a conclusion, and when simplicity of speech obscures the complexity of argumentation that requires strict mathematical verification. His distinction lay in linking clarity with intellectual honesty, defending the public's right to understand the grounds for choosing particular scientific routes. His style of problem-solving arose from belief in the power of minimal principles as a way of knowing and testing reality. The reason for this stance was the idea that the fundamental laws of the world gain meaning through simple but deep postulates that then reveal a wide class of phenomena. The method's arrangement relied on thought constructions, sensing invariants, and searching for those postulates that withstand translation into different contexts. The consequence was the ability to move from small foundations to large-scale conclusions and to construct theories possessing an internal restraining logic. The limits of this approach appear in the risk of excessive abstraction, when chosen principles require specific clarifying formalization for predictive power. The distinction was that he demanded from principles not only logical beauty, but also clear empirical bridges to observation. Intuition and formalism in his work operated as complementary ways of searching for truth, since the idea that mathematics serves as the language of thought combined with attention to imagistic representation. The reason for this combination lay in the desire to make theoretical constructions comprehensible to minds capable of operating with visual and semantic schemes. The device of translating abstract equations into imagistic constructions included a series of intermediate intuitive steps that allowed assessment of the plausibility of a result before full formalization. The consequence of such an arrangement was an expanded possibility of communication between experts and the wide circle of interested people, and an increased motivation for experimental verification. The limits of the method manifested when metaphorical representations assumed the status of final conclusions, and when the understanding of the need for rigorous mathematical refinements was lost. The distinction consisted in the insistence on preserving the critical character of images. Images were a prompt to verification, not a replacement for it. Aesthetic criteria served for him as epistemological orientation, because simplicity and coherence of an idea often acted as indicators of its fruitfulness. The reason for this orientation consisted in the sense of consonance between natural regularities and mathematical clarity. The way aesthetics were applied consisted in choosing hypotheses that trace a minimal number of postulates while maximally covering phenomena. The consequence was the emergence of theories capable of unifying heterogeneous facts into a single system and stimulating further research. The limits of the aesthetic approach became evident when the beauty of ideas began to displace critical verification, and then preference for a beautiful solution led to ignoring contradictory data. The distinction manifested in a constant demand to combine aesthetic appeal with the requirement of testability. Personal qualities shaped the work rhythm and scientific priorities as strongly as intellectual convictions, because plain modesty, strong curiosity, and stubbornness served as sources of creative perseverance. The reason for this interconnection lay in the fact that character determines the mode of intellectual search. The habit of prolonged concentration and patient doubt shaped the style of problem solving. The mechanism of personality's influence manifested through the choice of questions, readiness for prolonged criticism of one's own ideas, and the habit of public clarity. The consequence was that the personal stance strengthened trust in judgments and at the same time generated expectations of moral responsibility from the scientist. The limits of this influence are where individual traits begin to dominate over the collective nature of science, and when the legend of personality obscures collective efforts. The distinction is expressed in that his personal habits were aimed at serving the idea of knowledge and the public conversation, not at cultivating the myth of a hero. Social habits, mentorship, and public appearances functioned as mechanisms for transmitting scientific culture, because science preserves and multiplies itself through people and institutions. The reason for attention to these aspects lay in the conviction of the importance of forming not only professional skills, but also a civic attitude toward knowledge. The transmission apparatus included delivering lectures, participating in discussions, and readiness to discuss values related to the practical application of discoveries. The consequence of this practice was the expansion of notions about the scientist's role as a participant in public dialogue, and the formation of educational standards
where critical thinking is viewed as a key skill. The limits appeared in the risk of creating a cult reputation and in the possibility that an individual image can shift attention away from collective research. The distinction was that public activity was directed at supporting institutions and developing discourse, not at personal popularity. The legacy of his ideas includes both real technological consequences and the change in the ways questions are posed, since the meaning of formulas and principles often goes beyond immediate calculations. The reason for this double effect is that fundamental principles set benchmarks for measurements, instruments, and practices, as well as for methods of thinking. The mechanism for translating ideas into practice implies producing predictions, creating methods of verification, and implementing results into technical solutions. The consequence of such translation was changes in measurements, navigation, and understanding of cosmic processes, as well as in the general culture of scientific thinking. The limits are visible where historical applications deviate from the moral context of the original ideas, and when technologies are used for ends not commensurate with the initial ethical stance. The distinction consisted in the persistent reminder of the links between theoretical honesty and practical responsibility. Applying his approach to contemporary dilemmas requires institutional forms that preserve the critical autonomy of science and ensure society's participation in risk assessment. Because the speed of technological change sets a new tempo for social expectations. The reason institutions are necessary is that a single voice, however loud, cannot replace a systemic mechanism of discussion and control. The structure of such institutions should include transparent procedures for expert evaluation, consultation mechanisms, and help in translating complex conclusions into comprehensible guidelines for decision-making. The consequence may be a more measured policy in matters where technologies change living conditions, and a reduction in the risk of ill-considered decisions. The limits of such efforts manifest in the difficulty of international agreement and in conflicts of interest that require political will and diplomatic effort. The distinguishing feature of the model is that it regards scientific honesty and public responsibility as organically linked elements of the political process. Points of distortion arise from oversimplification of ideas, a culture of heroization, and the translation of scientific images into popular symbolism, because each translation carries the risk of losing nuances. The reason for such distortions lies in the fact that mass perception tends to seek concise symbols and spectacular formulas that are easier to receive and spread. The mechanism of distortion includes turning complex argumentation into aphorisms, replacing strict clarifications with images, and the tendency to associate authority with personality. The consequence is erroneous expectations of science, superficial understanding, and political decisions based on a simplified notion of a theory's capabilities. The limits of combating distortions are connected with limited resources for enlightenment and with the speed of modern communications. The distinction of his approach consisted in trying to resist simplification through methodical explanation and by appealing to critical thinking, rather than through the defense of personal authority. The assembly of this thinking forms a coherent picture in which philosophical foundations, methodological practices, and moral responsibility are interdependent, because the meaning of scientific inquiry is determined simultaneously by the striving for explanation, foundational commitments, and social context. The reason for the coherence lies in the fact that the choice of methodological starting points sets both the framework for discussing moral consequences and the possibilities for communication with society. The structure of this coherence consists in the constant translation of abstract principles into a form suitable for verification and discussion, and in returning from social consequences to the refinement of theoretical premises. The consequence of such work is the formation of a culture of scientific dialogue, in which knowledge is linked to the obligation to explain and to the readiness to take social consequences into account. The limits of the coherent picture manifest in the demand for continual self-purification of theory and in the risk that social dynamics impose a tempo incompatible with the measured development of ideas. The distinctiveness of his approach lies in that he proposed a model where scientific rigor is combined with moral reflection, and where enlightenment is regarded as an integral part of the scientific mission. A short summary rests on several key ideas that help interpret his legacy and apply it today. Simplicity as a method serves as an epistemic compass, guiding the choice of postulates. Intellectual honesty requires openness about the limits of one's positions and a commitment to verification. The responsibility of the scientist lies in actively participating in discussions of the consequences of their findings and in supporting institutions capable of translating knowledge into policy guidance. Enlightenment is seen as a long-term task aimed at cultivating critical thinking in society. The delineation of authorities helps to understand where technical competence gives way to the realm of value choices. Willingness to engage in public dialogue remains a practical prerequisite for reconciling science and society.
Reading him today requires simultaneously working with principles and their limits. Requires the ability to see simplicity as an invitation to scrutiny rather than an end in itself, and requires readiness for collective discussion of the values that accompany the power of technologies.